Hello my people, hope we're doing well today. This is video 4 of those cumulative problems. I don't remember, this one was given back to my AB kids in 2013-2014. It's got 4 pieces. You see the graph. It's a cubic, and I've given it to you in factored form, so that ought to make sense out of this cubic, which has a zero of tangency right here because of the multiplicity at x is equal to 0. And then it has, of course, a multiplicity of 1 here at x is equal to 3. The negative out in front ought to make sense out of the end behavior of that particular function as well. Let's go ahead and look at part A. Now notice that the intersection of the linear and the cubic function create 2 regions, right? 2 separate regions. So if I'm asked to find the area between the curves, I'm being asked to find both of them. Now, let's go ahead and look at it without all the verbiage. If I am asked for that, I know, and let me go ahead and, as we're accustomed to do, color code these bad boys. The pink, of course, is the linear, and the cubic is our green one. Okay. Now, there are 2 points of intersection, and we need to, or 3 points of intersection. We need to find all 3 of those. Now, one of them is already found for us. We know that both of them have that 0 right here. Okay. So when we're dealing with that, we need to find this 0 and this 0 over here. Now it looks like -1 and 1, but let's go ahead and confirm that algebraically, okay? So we have negative x squared times x minus 3 is equal to negative x plus 3. But if I factor out a negative, I can get this, okay? Which, is kind of neat, because then if I go ahead and gather these on the same side, it almost looks like I'm halfway through a factoring by grouping problem, okay? And if I have 2 terms, I can notice that the x minus 3 is common to them. And so if I have x minus 3, then I'm going to get negative x squared plus 1. Or if I pull out a negative 1 as well, I get x squared minus 1 is equal to 0. Okay. Now what that means, of course, since basically numerical factors do not impact zeros, is I have x plus 1 and x minus 1, and therefore, what I eyeballed on the from the graph is correct. My points of intersection are -1, 1, and 3. Okay. Now, that is going to determine our limits of integration. And because we have 2 regions, one of which is defined from -1 to 1, with g of x being more positive, my one from -1 to 1 is going to be g of x minus f of x. From 1 to 3, I have f of x being more positive, and therefore it's going to be the integral of f of x minus g of x. So let's go ahead and set that up. Go from -1 to 1, okay, and I need my more positive one, negative x plus 3, minus my more negative one, which is negative x squared x minus 3. I should have used braces, but whatever, you get it. Basically, I've used parentheses enough to where you should be able to discern what's going on there. And I need to go from 1 to 3 of negative x squared x minus 3 being my f of x minus my g of x. Okay? And those 2 integrals together added up should give me what I need, okay? Now, let's go ahead and pause for just a moment, okay? Now, if we have g of x minus f of x, okay, that means that we have negative x plus 3 minus negative x squared x minus 3. Now, you could do it by factoring, I guess. I mean, basically, if you wanted to do that, you could pull out a negative 1 right here, and that'd be x plus 3. Basically, those two negatives cancel each other out, x minus 3. And then, of course, basically, we don't want to factor it. We actually want to multiply it out so that it's in polynomial form. Because if it's in polynomial form, we're going to be able to integrate term by term. Now let's put it in descending order, the way that it should be. Oh, by the way, this, if I factor out a negative 1, that should be x minus 3. Why I did that, I have no idea, but whatever. And of course, we have x plus 3 in the end. So that is our cubic function. That is our linear minus our cubic, which of course creates a different cubic. And if that is g of x minus f of x, then f of x minus g of x should be its negative, right? 3x squared plus x minus 3. Okay, well, let's go ahead and integrate that. Now we know that the first one was, of course, our g of x minus f of x, so our negative 1 to 1. We need it to be this one right here, so that's our x cubed minus 3x squared minus x plus 3 dx. And that's going to be equal to, 1/4 x to the 4th minus x cubed minus 1/2 x squared plus 3x from negative 1 to 1, right? And then we just have to plug it in. Okay, when you plug in 1, you're just going to get 1/4 minus 1 minus 1/2 plus 3. When you plug in negative 1, you have to be a little bit careful because obviously plugging in negative 1 into the first and third term, it's going to turn back positive again. But in the second and the fourth term, it's going to have an impact because those are odd degree. So we have 1/4 plus 1 minus 1/2 minus 3. Well, let's go ahead and distribute this negative, okay? And that means that this 1/4 and that negative 1/4 cancel out. That negative 1/2 and that positive 1/2 cancel out. And we have 2 plus 2, or 4. Let's go ahead and do the second integral that is part of our area problem. And of course, it's the same integrand, just negativized, okay? And therefore, it's going to integrate in much the same way, right? It's going to basically, its integral is just going to be the negative of the integral above. So there's not a whole lot of work being done here except for just sort of copying stuff down. And this goes from 1 to 3. Now this is going to be a little more difficult in terms of the computation simply because you're plugging in 3 rather than 1. But 3 to the 4th is obviously 81. So we have negative 1/4 times 81 plus 27 plus 1/2 times 9 minus 3 times 3. And then we're going to subtract, plugging 1 into there, which is going to be 1/4 plus 1 plus 1/2 minus 3. Now, this right here is negative 81/4, okay? Negative 81/4 plus 27 plus 9/2 minus 9 plus 1/4 minus 1 minus 1/2 plus 3. Now, thankfully, a lot of these are going to be grouped together rather nicely. The negative 81/4 and the positive 1/4 gives you negative 80/4 or negative 20. Okay, so we'll cross those off, not because they cancel, but because I've already done the arithmetic. And now let's do the halves. 9/2 minus 1/2 is going to be 8/2 or 4. We'll cross those off because we've actually done the arithmetic. And then 27 plus 3 is 30, minus 9 minus 1, so minus 10. So 30 minus 10 is, of course, 20. and this one is also 4. So the total area for part A is going to be 8, okay? So basically, this right here winds up being 8. And you go, see next page, right? Okay. Now, that was part A, and that was actually quite a bit of legwork just for an area between the curves. But sometimes they're easier than others, okay? Let's go ahead and look back at the original problem again. Now, part B asks us to find the average value of f on the interval 0 to 3, okay? And then it asks us, of course, a mean value theorem of integrals question in the rest of B. Now, since I'm not dealing with g of x, I'm only dealing with f of x. What I've done is I've actually gone ahead and printed out just the cubics so that the linear doesn't get in our way, right? And if we're finding the average value from 0 to 3, it's basically the average value of this area right here between the zeros, okay? So if we're going to integrate from 0 to 3, our f of x, right? We get negative x squared x minus 3 dx. And then, of course, we need to divide by the width of the interval, which is 1/3. Now, thankfully, this, in order to get it in polynomial form, all I'm really going to do is just distribute that negative x squared. It becomes negative x cubed plus 3x squared dx. Okay. Well, let's go ahead and integrate that. We have 1/3, since the constant always just comes along for the ride. And I have negative 1/4 x to the 4th plus x cubed, and I'm going to be evaluating from 0 to 3. Well, it's one of those nice ones where I don't have to evaluate the 0 because it's in polynomial form, and every time I plug in a 0, it's just going to give me 0. But let's go ahead and let's evaluate the 3. It's negative 1/4, and we've already done this evaluation. It's negative 81/4 plus 27, and that's when we plug in 3. And then, of course, when we plug in 0, we get 0. Now, what happens here is this becomes 1/3 times negative 81/4, which is negative 20 and 1/4, plus 27. Well, 27, if you want to put it in terms of force, is 108, right? And so what we have here is negative 81 plus 108, which is positive 27. So I have 27 force times 1/3, which just gives me 9 force. Okay. Now that is the average value. What I need to discern now is there a value of the function where that is actually going, where there has to be, right? Because it's continuous on the interval. What I need to do now is I need to determine where this average value is equal to the output here. Well, 9 force is 2 and 1/4, and so let's go ahead, and if that's 2 right there, because that's between 1.6 and 1.8, if this right here is 2, and this right here looks like it's going to be 3, because they've scaled this weirdly on this little program. 9 force, 9 and, 2 and 1/4, this is 2.2 right here, so it's basically just a little bit above there. And so I'm looking for this point and this point, okay? Okay, well, let's see if it actually works out. I have negative x cubed plus 3x squared is equal to 9 force, right? Or, really, let's do it the right way. And actually, let me get another sheet of paper since this is kind of running over a little bit. Negative x, I did it again, negative c cubed, okay, negative c cubed plus 3c squared is equal to 9 force. Now, what happens here is basically I need to go ahead and multiply through by 4, and you get 12c squared is equal to 9, and you get 4c cubed minus 12c squared plus 9 is equal to 0. And actually, you know, I don't know if there's even a way to do this algebraically. Let's go ahead and start working with the calculator to confirm kind of everything that we've seen thus far anyway. Now let's go ahead and go to y equals. We have negative x squared times x minus 3, okay? And our average value is 9/4, right? Let's go ahead and go to the window, and we'll do it from negative 1 to 4. And our y, let's go negative 1 to 5. And we see our cubic. And now we see our constant function, which represents the average value. And let's go ahead and let's just find the let's just calculate the intersect, okay? Go down here, get close to this one, get close to that one, and it winds up looking like our first value for C is 1.084. 1.084, okay? Let's go ahead and calculate again, and we'll go ahead and breeze on over here towards the other point of intersection. Equals, and we have C is equal to 2.689. 689. Okay. Now, let's, I mean, time is running short, so I mean, you get the idea on this one. Let's go ahead and move on to part C. Okay. Oh, part C says there are two regions created by the function above. Now, thankfully, C and D aren't going to take that long because it actually doesn't ask us to evaluate anything. It simply asks us, notice the italicized words, to set it up, okay? There are two regions created by the functions above, set up but do not evaluate the integral representing the volume of the solid created by revolving both regions around the x-axis. Both regions. Now, neither region, except for at this one point right here, is tangent to the axis of revolution, and therefore on both I'm going to have a big R and a small r. I just have to discern which is which, right? Now, this right here is g of x. This right here is, of course, f of x. So, if we are looking for, and let's go ahead and just do the integrals separately, okay? If we're looking for, and let's go ahead and label it. Let's call this first area area A and area B. So we're revolving A, and over here we'll revolve B, okay? Now, in region A, g of x is more positive. We recognize that when we did the area between the curves. But it's a little bit different here because we're identifying the one that's farther away, because we're not going to subtract one function from the other. We're going to subtract the square of one function from the square of the other. Because our big R for revolving A is g of x, which is negative x plus 3, and therefore big R squared is negative x plus 3 squared, right? Which is the same thing as x minus 3 squared, and you're going to get that, okay? Now, my small r, and the thing is that you can put it in that form, you can not put it in that form. If I was actually asked to evaluate, it'd probably be better to go ahead and have it in that form, but I'm just asked to set it up. My small r is going to be my f of x, which of course is negative x squared x minus 3, and therefore my small r squared is going to be negative x squared x minus 3 squared, or x to the fourth x minus 3 squared. Now, that is my small r. So remember that when I'm dealing with revolving it, I need pi out in front. I need my limits of integration, okay, pi out in front. My limits of integration for region A are -1 to 1, and then I need big R squared, which, we can rewrite as that, minus small r squared, which is that, dx. Now, this one ought to be considerably easier because, basically all you're doing is just changing the limits of integration and swapping big R and small r. Because in this case, big R is going to be f of x, because it is more positive, it is farther away, so it is going to determine the outside circumference of each washer cross section. And therefore big R squared is going to be -x squared x minus 3, the whole quantity squared, which is x to the 4th x minus 3 squared. Now, just like in the last one, basically just like this one, it's going to be swapped, and so small r is g of x, or -x plus 3. And of course, when you square a difference, you might as well be squaring its opposite, because the negative gets sort of unnegativized, right? And therefore, the integral for this one, remember to change your limits of integration, goes 1 to 3, is basically the flip, the opposite of that difference right there. So x to the 4th x minus 3 squared minus x minus 3 squared dx, and of course the total volume is those two integrals added together. Now, the very last piece of this problem, okay, is going to be set up, but it's going to be volume of a solid of known cross section. So it says, set up but do not evaluate the integral representing the volume of the solid created by the region in the first quadrant bound by F and the x-axis having equilateral triangle cross sections. Okay, so this one, again, we're going back to, just like in B, something to do with F, and so I went ahead and printed another one of these out so that we can sort of ignore G, and basically it's going to be vertical cross sections for an equilateral triangle. And remember that basically you need your constant, whatever your constant is, from A to B, of whatever your S of x is, so basically the side that is determined by the region, side squared dx, right? Well, in this case, it's equilateral triangles, so you know that your constant is √3/4. It's from 0 to 3, okay, because it says the region in the first quadrant bound by F and the x-axis, and this is the only region right here, in the first quadrant. And now you need S of x. Well, S of x just happens in this case to be f of x. So it's -x squared x minus 3 squared dx. And that right there will give you the volume of sort of equilateral triangle cross sections, which create a solid with this region in here as the base. Okay, and that is part D. Now, A and B took us a little time, but because C and D were just setting things up and not integrating, those went much faster. Okay, and that's kind of nice. That brings us to the end of this particular video. I have one more video on a cumulative problem, and then I'm going to do one video which basically takes a region from between two curves and revolves it around different axes, because I'm hoping that doing that will sort of help us understand the revolution stuff a little better, basically. But if you have any questions, please do shoot me a message, email, chat on Teams, whatever. Bye.